Hi everyone, I'm Atefe, and this summer I worked with Dr. Chidem Osoy on the substrate effect on optical properties and exfoliation behavior of chalcogenide material. So during this project, our main focus is to understand how different substrate metal oxide can affect the surface plasmon property of chalcogenide, three different chalcogenide material that we are working with them, which is molybdenum disulfide, bismuth selenide, and bismuth telluride. So what is chalcogenide material? Chalcogenide material has at least one chalcogen anion in their structure, and also at least one electropositive elements. And some of properties that they have a band gap between 1 to 3 electrovolt. They are superconductor and thermoelectric. They are also topological insulator, and they have surface plasmon. So we are interested in surface plasmon to understand how this substrate can affect this surface plasmon property and change it. So what is surface plasmon? Actually, plasmon is the oscillation of free electron in the plasmonic environment, and the plasmon surface or environment is the common area between a dielectric and metal. So in this project, we have two different steps, fabrication part and analysis part. In the fabrication part, first, I will create two different metal oxide as a substrate, which they are silicon dioxide and aluminum oxide with the atomic layer deposition to do mechanical exfoliation of chalcogenide material that I have on them. And in the analysis part, after creating this film, I will go and measure their dielectric constant, thickness, index, and roughness with ellipsometer and atomic force microscopy. Also, after exfoliation process, I will measure the surface plasmon of exfoliated particle and the surface with Raman spectroscopy. I also use a scanning electron microscope and optical microscope to take picture of my film surface. So in the first step of that fabrication part, I used silicon dioxide wafer as underneath, and after that depositing two different metal oxide, silica and alumina, which both of them are hydrophilic metal oxide. And the reason that I choose these two hydrophilic material, because hydrophilic materials are charge polarized and they are react with polar substances, which my chalcogenide material also are polar material. I assume to create these films in three different thickness, 10 nanometer, 15 nanometer, and 100 nanometer, to see how their thickness can affect also surface plasmon. In the ALD machine, when we want to, I told you that I assume to create this thickness and how I do that. So each cycle is a specific amount of that film when I create with ALD machine. In the ALD machine inside the chamber, so in one cycle, there is a pulse of gas that we release and waiting time, then a pulse of water, and also waiting time to create the alumina film on the surface. And this cycle repeat. For example, for alumina, the gross amount per cycle is 1.1 angstrom, and according to this data, I can go and set up the machine to the desired thickness that I want. Here, after I create my film, I took some pictures from the surface with SEM. So that one is SEM pictures that I took from silicon dioxide, wafer, and alumina. And here, these two pictures are AFM pictures to measure the roughness of the surface, which also in this picture show that alumina has more uniform surface than silicon dioxide, which alumina is 142.5 picometer, less than silicon dioxide, which is 203 picometer. After creating to understand how that thickness can affect the exfoliation behavior of bismuth selenide, here I did that exfoliation on the surface, and according to this picture that I took with optical microscope, you can see as I increase the thickness of the film can absorb more particle of bismuth selenide on it. Here I also, after that, I added some methods to understand how heat and cleaning, solvent cleaning, and oxygen plasma can affect the exfoliation behavior of my material. So in the first method, I just did direct exfoliation without adding anything. In the second one, I added 100 degrees Celsius heat. In the third method, I added solvent cleaning, which is acetone, methanol, isopropanol, plus oxygen plasma cleaning. And in the first one, I added all together: solvent cleaning, oxygen plasma, and heat. So here is the result that I took picture from adding and applying that methods to my films. Here is 100 nanometer silicon dioxide in 4 methods. The first method was adding nothing, and the second was just heat, third one solvent cleaning and oxygen plasma, and the first one all of them, which is there's not that much difference between all methods, but these pictures show in the second, third, and fourth one I have actually similar amount of exfoliated particle, but in the first one I have less, where I did not added anything. I have less particle on the surface. This one is same process on the alumina, 100 nanometer alumina. For the alumina, it shows where I added oxygen plasma in the third method. Actually, surface absorbed more exfoliation particle and bigger particle on the surface, and show oxygen plasma makes some difference in alumina surface. I was explaining that I create that 2 film, silicon and alumina, but actually I could not find any thin layer that I was working, and I did the same process on the hafnium dioxide film that I already created. This is 7 nanometer hafnium dioxide film, and I could find a thin layer of bismuth selenide on the surface. As you can see here, I have pretty thin flake of my bismuth selenide, and I took this flake to measure with atomic force microscopy machine. Here I did a 3D picture and measured the edge between bismuth selenide flake and hafnium surface to understand how thick is my founded particle is, and it showed it is 2.82 nanometer thickness, which is exactly 2 unit cell of bismuth selenide. This is 1 unit cell, the structure of 1 unit cell bismuth selenide. And when we expand these 2 unit cell of bismuth selenide, this is exactly the structure in the flake that I found over there. We can say we have 2 unit cell in that structure, or 3 quantable layer, which each quantable layer is 1.94 nanometer, and in the structure of each quantable layer, we have 3 layer of selenium and 2 of bismuth selenide. And all these quantable layer keep together with a van der Waals force. So during this project, I understand that silicon dioxide is really better underneath film to exfoliated bismuth selenide, and there wasn't that much difference between the other methods that I added, but it showed that oxygen plasma can make some changes and make surface sticky to absorb more exfoliation particle. For the future work, this was just the beginning of my project and I could not finish my project yet. In the future work, I will do the surface plasma measurement for silicon dioxide and aluminum oxide to compare them and do the same process for mobidium disulfide. And thank you for everyone who supported me during summer and helped me for my project. The sources that I have. Do you have any question?